Hello, you guys. Sorry, habitually late here. How habitual is this, and how late am I? Let me check it. Let me check. We got 13 people. That's good. AIM is in the building. That's good. Thank you. And we're missing Ethan. Is Ethan here? Ethan always comes up. He's like me. He's not as punctual, right, as I should be. Oh, right. What we have on the board is our next topic. No, this is my other class. I have zero break between the two, but that's okay, right? It's the thrill of the thing. Anyhow, this is for those that are computer science majors or math majors in the know, that what I'm teaching or trying to teach in the algorithms course is the concept of dynamic programming. And if you've never heard of that, it's kind of like linear programming, right? Nothing to do with programming computers. It's nothing to do with that. It's older than, it predates computers. But this is a dynamic programming algorithm, and that's presented in the textbook. It's order n cubed. And I was trying to show over here, I told people that it's been shown by some researchers that you could do it in n log n by transforming a problem into a problem about the triangulation of polygons. So now we're back on ground that maybe teachers might know. When you took geometry, isn't that still required for teachers? Did you talk about triangulations of polygons?
Yes, we have to, even just as a part of your bachelor's, you have to take Math 370, which is geometry, which goes pretty advanced in terms of like how far in geometry you go.
Did you do non-Euclidean geometry in there, or just?
Yes, we had to do two. We had to do spherical and hyperbolic geometry as well.
That's
curious. Granted, it was kind of a baby's first introduction to, it was very much, if you want to keep going on this, you're going to have to do it in your master's. But we did get to see it.
The more I learn about your, you and others, and Ethan, tell me about what your experience was as a math major. I'm getting more and more impressed at the exposure you've had to a lot of major parts of mathematics. I mean, I feel like, it seems like normal math majors don't take that geometry class, so they would miss out on a lot of stuff.
Yeah, I noticed that it's not part of the regular math thing. It's part of the math for teaching specifically. And I have a feeling part of it is to, like, I have a second cousin who's teaching at Glendale Community College, and he let me know what you need to be able to be a community college teacher. And if you didn't get that as part of your bachelor's, you're going to have to go back and do it again anyway. So I have a feeling that's kind of what CSUN's doing, is making sure, well, if you do want to go and become a community college professor, you're going to need to take these courses regardless. So
I hear you, and it's a good thing. But I can tell you a bad thing that sometimes happens. I have heard that sometimes community colleges are biased against hiring people with advanced degrees. Like if you have beyond a master's, or you have master's plus other things, they don't like that. They don't like that. If you're a PhD, they don't like it. I don't know what the real reason is, but
is it because they're scared you're going to move on or something?
No.
Okay.
Nobody moves on from I'm sorry to say this. I probably get in a lot of more trouble than I already am in, but people like community college teaching career because committee work is reasonable. You don't have PhD students. You don't have master's thesis students. You don't have the number of deadlines you have. You basically are you're hired to teach. Not to do research. And the old thing, publish or perish. Well, if you don't publish, there's different ways of perishing, right? You can perish from overwork or trying to do what is some impossible thing. You know what I mean? So it's very community colleges. I'm jealous of your relative or your friend. That's a very desirable career. And speaking to some computer science majors in this class right this moment, you guys, you know that computer science is going to start getting taught in the high schools, which means it's going to be taught even more so in the community colleges. You could consider
that's a big thing going on right now. Is right now, if you want to teach computer science in high school, you don't need a computer science degree. They grab it from like a math person. They're changing that. Yes. I'm so excited about that. I think that's fantastic.
But I'm speaking to your math major. I'm speaking to the computer science guys, and maybe they didn't think about secondary teaching, as a,
Right. Yeah,
because
it's
of the
now
stories I
viable. It's a thing you can do.
Yeah. Well, there's this counterbalancing story, which I've already said to this class, I believe, that and when I taught this in summer, I told you about the guy that made $350,000 programming for Activision in 1 year. He did this, and excuse me, there's an alarm. Okay, so he was not happy about it because he was working 80 hours a week. But when you're young and and you're not independently wealthy, and you're saying, "Well, I save up for a house or something like that," you might be tempted to get an industry job, like in gaming. It's Activision. Then it's tempting because you can't, as a teacher, you're not going to make $350,000 a year, unless you're have Buettner's position. You know what I mean? So there's a lot of different trade-offs in this whole thing. But this guy, even though he made that money, he was not happy. He wasn't smiling, and he felt it took a toll on his health. And 80 hours a week, just it wasn't. I already told you that story, right? Before, right? Didn't I?
Not to this class. It doesn't sound familiar. But well, I'm with you on I don't want to be working 80 hours a week. That's for sure.
And the funny thing was, my class, I talked to this class, right? I mean, the same 340, but last, 2 semesters ago, whenever this happened. And I told them how hard it was. He got some liver dysfunction or something. It's like you get when you're under a lot of stress. So his doctor said, you gotta slow down. And I told the class this, and I said, would any of you guys, make this trade-off, money for health? And they all went, no, we would not make that trade-off, And guess what happened? And the next day, I got like 6 emails from students in the class saying, connect me to this guy. I don't know, man. It's just, this life is funny, right? I mean, that's funny to me that they would be quiet about it and then like agree that, no, don't do it. But when it comes to, they thought about it, then the greed factor comes in. Would I be tempted to work 80 hours a week? No, because I don't think I last more than 2 weeks. All right, okay. Let me get my pens here. Okay, so my memory it's not good, but something I wanted to do, but it seems like it keeps on getting put off if I didn't do it, is the variance of the uniform distribution. I felt like we did the expectation, which was obvious, it was in the middle, but we didn't do the variance. Is this correct? I think it is.
Okay. We actually have not done the expectation.
Oh.
I mean, it is obvious, but we haven't done it.
Thank you.
Yeah.
Again, why am I doing this? Because you know what I like to do? I like to do problems that are sort of applied and stuff. And then those constants, the constant in the variance becomes the critical factor, okay? If you're trying to simulate something. Anyhow, the uniform distribution is my favorite, for anything, It's it's non-normal, right? And you do these simulations with the CLT, the central limit theorem, and they converge. You see it right away, even though you're starting with the normal. You're starting with the uniform distribution. So let's see if I can figure this out. So X is hopefully not in the uniform alpha to beta. Let's make the calculation. I know I'm in the washout, but I think you understand what I'm talking about here. So the expectation is going to be what? Well, the density function for this is 1 over beta minus alpha. And we need to, because it's the expectation, I need to x times the density function. And it's 0 off of alpha to beta, so I do this. Okay. I have to adjust from the last class. I was giving it all my all in the last class, and now I'm slower. So anyhow, so this is what? This is x squared over 2 from alpha to beta times 1 over beta minus alpha. And hopefully we get the answer. What's the answer we expect? Here's alpha, here's beta. So here's that distribution. Now remember, that's a probability distribution, so it has to, the area under the curve has to be 1. And I already joked about this, did I not? In Math 140, this shows up on the standardized tests. And students complain about the test. They say, well, there was no distribution. They have the window, but I didn't put the curve in there. You guys get it, right? They're expecting to see. They think on the test that there's supposed to be some sort of distribution area. No, the curve is really simple here. It's of height what? It's of height 1 over beta minus alpha. This is this, so you multiply the two, and you get a triangle you get a rectangle with area 1. Okay. Let's see how many, we've got 19 people. Okay, now, well, I didn't finish it. So let's evaluate this. I have 1/2, and what do I have here? Beta squared minus alpha squared over beta minus alpha, which is equal to what? Well, this
back to the top.
Oh, sorry.
No, you're going to do it anyway. Back to the top.
Yeah, I'm going to do that in my head. So it'll cancel the beta plus alpha over 2. And that's exactly what we expect. We expect the mean to be in this. This doesn't look good. In the center of that. Now, doing the variance requires me to do some algebra, which I'm not good at, and it's notoriously tricky to get it right. I'm going to have to factor something, okay, a cubic or something like that. So just bear with me. But again, I find it so critical to have this constant in the variance. I need that constant, okay, for really good problems and the central limit theorem. That's the last thing we do in the class. That I feel like I must do this, even though I'll expose my lack of algebra skills. So to get the variance, what do I need? So to get the variance, it's the variance of these continuous random variables is the same formula. E of x squared minus the mean squared. E, the expectation of x squared minus the mean squared. So what we're missing here, we need to get E of x squared. Okay, so we've done this already. So what is it? Now it's going to be alpha to beta x squared. That's the formula. I don't know what proposition that was. I believe it was 2.1. 2.1 in Ross. So that when you have the expectation,
I don't remember what it is in the book.
Yeah, this is the formula. If you don't apply this proposition, it's quite difficult to get the expectation. So you take the function of x. So see, it would be normally just an x, but because it's x squared, you get an x squared over here. Dx. Now I have to integrate this quickly. So 1 over beta minus alpha times x cubed over 3. And what's this equal to? Oh, gosh. Well, I know. I'm just going to keep this around. That's going to hang around because I'm going to use it. Let's hang it around here. Okay. Now what? So it's 1 over beta minus, this is supposed to, okay, beta minus alpha times beta cubed over, so 1/3, this is 3 there, so beta cubed minus alpha cubed. Okay, so this is some sort of messy thing. So there's a 1/3, but then the beta minus alpha. Now I have to do again. I got to do something in my head. How does that factor? So
Okay. Well, I mean, I just know this one. If it's okay.
Yes, tell me.
Okay, you're going to get beta minus alpha, the quantity, times the quantity beta squared plus alpha beta plus alpha squared.
Yes, exactly. So, right. So, the beta minus alpha from this will cancel this, but the 1/3 remains. And so the top is beta squared plus alpha beta plus alpha squared. If I did this right, because we have this, but this factors out. So if we're trying to succeed in getting the variance, what will that be? It's going to be that quantity. So beta squared plus alpha beta plus alpha squared over 3 minus the mean squared. So that would be beta squared plus 2 alpha beta plus alpha squared over 4 because I'm squaring. And that looks like a big mess. So let me back up and try to write that a little bit better. So this is beta squared plus 2 alpha beta plus beta squared. That's the mean squared. So this is the variance, definition of variance. Now I don't know if I can do this as a one-shot deal with the space I have left, but I've got to think now, what is the common denominator going to be? I did all this to get that for a future exam problem. What is the common denominator? 12, right?
Yeah.
So we have 4. I don't know how well this will work. 4 beta squared plus 4 alpha beta plus 4 alpha squared minus 3 beta squared minus 6 alpha beta minus 3 beta squared. Three beta squared. All right. Oh gosh. Now I got to cancel some stuff out here correctly, which is the thing. So if I'm going to have to squeeze in the answer here. I know that in the bottom there's a 12, right? But how many beta squareds do you have? Well, there's 4 beta squared here and minus 3 beta. It looks like I have 1 beta squared. How many alpha squareds? Uh-oh.
1 alpha squared.
So alpha died in unexpected death.
You just wrote beta squared twice on accident over there. Yeah.
This is supposed to be alpha squared. And because of that, this was 3 alpha squared. Okay. That changes things, does it? Okay, so beta is okay. But what about my alpha squared?
We get plus alpha squared at the end. And minus 2. Yeah, minus 2 alpha beta.
Well, that is what?
That looks like a square.
It looks like alpha beta or alpha minus beta squared. So I don't know where to put it. So it's alpha minus beta squared over 12. That 12 was what I was going after. Let me see if it's right. Let me check if I did it right. Oh, I don't have the notes. I don't know. I assume it's right. I didn't bring the notes for this, so I assume this is right. So this won't show again until the test. I'll do something, I'll do something with this.
I just Googled it to be safe, and yeah, it is. They put beta minus alpha squared over 12, but whatever. It's squared. It's fine.
The number, I wanted that 12, because some people say, where did the 12 come from? Where did the 12 come from? Well, when you do these simulations, you can see it pretty quickly that it has to be, it's got to be there. Okay, so let's just do a. I know I'm jumping around, but I want to do another normal calculation just to because it's so fundamental. Let's just do it, okay? I know I'm reviewing the things that we already know, but that's just the way I learn. So let's do another standard, basic normal calculation.
Review is
I'll
fine.
jump around.
We like review. It's fine.
Well, but until I get the teaching evaluations, they say, well, it was too boring or we did the same thing 5 times or something like that, But this is how I learn. I don't. To me, it's not a linear process. Learning is not a linear process. And in fact, I don't even know what the process is when you get older. I'm afraid it gets a lot harder. So let's do this one. So X is normal, is mean mu, and parameter invariant sigma squared. And they're saying that in this case, this example in the book, this was 3 and 9. You have to be very careful between textbooks because most textbooks go mu sigma. They don't go mu sigma squared. So for most books, you would look at that 9 and say that's the standard deviation, or you wouldn't see anything because it's marked out. So let's do it here. Okay, and what we're supposed to do is compute this probability. Why am I doing this? Because it involves the absolute value. Why the absolute value? That's a bugaboo in later on in the problems coming up. So that you'll see a lot of this. Like there's some inequalities estimates, which I've forgotten the name right now for that. It's expressed in terms of deviation from the mean.
Just to be clear, that's greater than 6. So we're finding like the tails.
Yes, exactly. Exactly. Very good. Okay, and the fact that it's tails means that we can just add the two possibilities. But I want to share with people the procedure. Symbols unclear.
Can you just kind of go over like from the top what those are?
Okay, let me draw this a little better first. So this is normal with mean mu and a parameter sigma squared. And let me show you where these come in. You have to be careful. Again, Math 140 books or lower, sigma here. They don't go sigma squared. So when you just have the numbers, you'll not know how to do this.
But just as a reminder, sigma squared means variance.
It's the variance. Well, where is it? What is it really? So let's see if I can remember what the density function is. Square root 2 pi. Where do these things come in? Well, there's a sigma here. There's a sigma there. And e to the minus x minus mu squared over 2 sigma squared. Sorry, I'm getting the CDF in there now. So this is okay. So this is the density. So let's look at where are those parameters. So this is the mean, and this is what we're calling the sigma is the standard deviation. That's the density, and it has these two things. It's not just one. It's not like the Poisson, with this one parameter. This is a 2-parameter thing. What else to say about it? You really okay. Ideally, what you want is the simplest. The simplest density for a normal is when your mean is 0 and your standard deviation is 1. So in that case, what would it look like? Times e to the minus x squared, because mu is 0 in this case. So x squared over 2. And the table is built from the CDF of this thing, the CDF. So when you, let's put this on hold for a second, okay? So when you do the CDF, so what is phi of x? Okay, this is a CDF. You go from minus infinity to x, and it would be this 1 over square root of 2 pi square root of 2 pi times e to the minus mu squared over 2 du. Okay, so this your table is built of these, all the area underneath the density function up to x. Does this help at all where this is coming from, these normals? These are various normal distributions? This serious thing is, how do we start with suppose you have, suppose you have this. Okay, you have this. How do you transform this into a standard normal of this type right here? Okay, well, the transformation goes like this. You take the x's, you take x, the random variable x, minus its mean, divided by its standard deviation. Okay, and it turns out this is a standard normal distribution. So in order to use the table, regardless of where you started, we're going to have to do that here to evaluate this problem. We need to do this normalization of the x. Does it make any sense? I've got some chat here, maybe not. To everybody, pi. What's x to the 2? 2. Here, that's 2, or which 2? Or is that from before? Equals 2 sigma squared. Oh, this is sigma squared. Sigma is that parameter. Okay, is that so? This is a sigma. Sigma is a Greek letter, right? I guess I don't know how to. Sometimes I just go like this. It's not a 6. Brandon, are you okay, or have I still got something equals 2? 2 sigma squared. 2 sigma squared. Is that okay? The formula equals 2. Oh, this thing? Oh no, this is z. It's another random variable. Okay, so this is a random variable, and it's been transformed to be this other one. So when you do this, you transform it into a standard normal bit. It's standard to write it like that. A z. It's not a 2. It's called the unit normal random variable. And these things, these numbers, if your raw data is of the form, coming from x, then these are called the transformed or the normalized scores. Okay, so there is some transformation of you do sometimes change the random variable to you do that sometimes, especially with the normal. It's a transformation of it. Okay, any other further questions? So where were we on that problem? We have to do this because I have to use the table. We're going to have to make this transformation here. So I'll need some help. So we don't need this, but I do need this transformation here. Let's first of all, let's interpret the absolute value, okay? So if the absolute value of x minus 3 is greater than 6, that leads to 2 situations. That x minus 3 without the absolute value is greater than 6. This is one possibility. And what's the other possibility? Well, it could also be that the negative of this is it's greater than 6. So negative of that would be probably a negative x plus 3. That thing is greater than 6. If you put a negative sign in front of it. So again, we want to transform like this. X minus mu over the standard deviation. This is what I'm going to do. Forget the z-score. All right. Okay, this is how absolute value works, right? I mean, if you have absolute value y is greater than 2, so either what? So either y itself is greater than 2, or minus y is greater than 2. Those are two possibilities. As Annie was saying, these are two. What does it look like on a number line? So 0 gives 2. So you're looking this way, or okay. So this means minus y is greater than 2, then y is greater than y is less than minus 2. So it goes this way. So these are the two sides of it. How could this have played out differently? How could this have played out differently? And the problem, how could the problem be adjusted to make it look something different?
In the problem, we didn't have a greater than 6, we had a less than 6.
Yeah, so that's right, very good. Right. So that's the other option, but that wasn't the problem in the book, so I'm trying to stay with, the notes. I mean, trying to use the notes, the book faithfully for notes. So anyhow, what do we do now? Well, let's write these two things out. So that's the probability that what? X is, add 3 to both sides, is greater than 9, plus the probability of what? Now I have got to figure this out. So this is, what is that? Minus x is greater than 3, but that's equivalent to x less than minus 3. You have to change the direction of the inequality when you multiply both sides by a negative number. So minus x is greater than 3. X is less than minus 3. Okay, now I have to do this stuff. So you'll be able to use the table. So what is this here? So I need to, the mean is 3. So I take x minus 3, and the standard deviation is 3. We've got to do the same thing to one side as to the other. So 9 minus 3 over 3. Plus this one. So the probability of x, so I need to go x minus 3 over 3. It has to be less than minus 3. Well, this took a lot more work than I thought it would do. And I don't want to be making any mistakes here. So this is probability of what? That now is a z. So z is greater than 2. 9 minus 3 is a 6 over 3. Plus the probability. Now what's this? Did I forget to do this? I forgot to. I'm doing this one right here. I need to do the same thing. X minus 3 over 3. Okay. I have to go minus 3. Now I subtract off 3 divided by 3. So what is this? So probably the z is less than minus 2. Hopefully we got that right. I better check this to make sure it is right. So it's supposed to be z is greater than 2 and z is less than minus 2. Yes, this is correct. Okay, so now to use the table. So we've done the normalization. So we use the table, and how do we do that? Well, let's look for some symmetry here. So So this is 0 because we're standard normal. So that's 1 and this is 2. So it's either that over there or over here. So it's a little bit on either side. So how do we do this? You could go, okay, you could get this portion right here by looking at 1 minus phi of 2. Okay, so phi of 2 would be everything coming up to here. But if I took 1 minus that, I would get what I want, this little right-hand portion. Let me look at the chat, make sure people are following me. I think they are. I think I'm the only one that's... and now, but there's 2 of those pieces, so you go like this. So I need to evaluate 2 times 1 minus phi of 2. And let's, instead of looking this up on the table this time, let's just quickly get an approximation to that.
25%.
Yeah, let's figure out what. So, phi of 2. Yeah, what? 95%, but it also has to have this little piece over here, right?
Right. Well, but 95% is from -2 to 2.
Right, but when you take phi of, I'm supposed to evaluate phi of 2.
Okay.
Oh, so you're taking the whole thing minus
yeah. I mean, that's just kind of where I'm like,
yeah,
oh, well,
okay.
I know that part.
Yeah, I was actually trying to get this. Okay.
Sure.
So, yeah, okay, so 95%. 1 minus 95%, so 5%. Right, because this is, by the rule, this is about 95%. And we're talking about everything else. So your answer is 5%, right? N'est-ce pas? Right? So it's, but if we do it by the book, if we go by the book, I have to know what phi of 2 is exactly, or better. What is phi of 2?
.5%, I think. Or wait. Let's see here.
What is that? 0.0228. So I'm getting 4.0458 645.045. So yeah, 4.56%. So around 4. Yeah. Okay. Sorry for all the detail, but if you use the table, that's what I get. So how close were we? Well, we're in the ballpark, but this is what they expect as an answer. Let me check the.
So I mean, I'm actually kind of curious on that one. So 95% is not an exact amount; it's an approximation.
It's a rule of thumb.
Okay.
It's a rule of thumb, and it's I've talked to statisticians, and they say they always go back to it. That's why they have these things sort of memorized, right? And so they always use z-scores, and then they can tell you,
right.
You get rough estimates for things. And I've heard different. Somebody was in that meeting I was in earlier today. I went to something about teacher education council or something, and it's sort of a pony show. It's a dog and pony show, and people are boasting about what they did. And some contributor had done a test, a significance test or something, and he said that his result was more than 1 standard deviation away from the mean, and he thought that was significant. So can we look at that here? Can we look at what that would mean? So, okay, I'm going to erase this. I know, I'm always nervous when people boast because I feel like that means there's pressure. There's some sort of pressure to get a result. And when if you're a statistician, you don't want to succumb to that. You might have, you might get, what do you call that, inconclusive result from your test, right? But I've noticed that when grants are at stake, funding is at stake, people sometimes exaggerate their results. And so this is the situation. The result he got was he got something. This is what he got. 1 standard deviation away. But the thing is, how do we interpret that? Well, how likely would it be by chance to have gotten a result like that or more extreme. Okay. So how do you interpret that? This is 1 minus 1. So you have to calculate that area. Did you follow me here? So he said his result was 1 standard deviation away. He was boasting about like this means his program is effective. And it's a way of teaching math. He said he has a new way, effective way. And you have to be careful when you set up experiments. You have to select randomly for any kind of treatment. Otherwise, you might end up selecting people that would benefit no matter what. You know what I mean? They're already strong students, and you have this new way of teaching math, they'll benefit even more. But anyhow, assuming that he did have randomization in the subjects selected, he said that there were 7,000 subjects because they're using standardized tests to measure, whether the new method of teaching math was good. So anyhow, how likely would it be by chance to get the result here or something more extreme? You tell me. Well, we already went over this. So how much is between here and here? Approximate.
68%.
68, right? So that means in the arms, how much do you have there?
16 and 16, I think was.
Exactly.
Hold on.
Very good. No, you're right. So look, can you put it all together? Well, how much is this? 16, right? Would you say that that's strong evidence that this procedure worked? I mean, by chance, if your experiment could have, in the null case where it doesn't do anything, would have generated a result like this 16% of the time. I don't know. I would accept 16% as something important to report, but I wouldn't bet my life on it. It's you round up to 20%. It doesn't sound.
Yeah, it's like a 1 in 6 chance of it just being, it just happened that way instead of it being
the result of the efficacy of a new way of training people to learn math. And another thing, I'm sorry to get off on my thing. This guy, I don't recall that there was any math faculty or involved in the program, especially not the statistics. So I just that's one good reason for learning some basic statistics. So when somebody's saying something, like a margin of error or something like that, did you understand what that means?
Oh yeah. I mean, one thing I did when I was doing some tutoring for a student doing statistics. Whenever you're looking for it, you can find like news reports that are like really reporting things with statistics in a really bad way. And so anytime that I would, I'd be like, oh, hey, check this out. So when you're looking for it, you can find it all over the place. So I really feel like it's all the more reason that we should at least have some statistics in high school. Before you graduate, you should be literate in reading stats.
I agree. There's a book about how numbers get bent or in statistics sometimes. I forgot the name of it, but it's very famous. I forgot it. It made some dramatic claims, which I think were walked back quite a bit over the years. One of them was they said that the academic success of a student depended heavily on how old that student was when they entered kindergarten. And literally, if there was a few months difference, it showed up on the back end. It's amplified tremendously. You guys are familiar with this? Because if you were older, I kind of get the thing. I think if you were older going into kindergarten, you would absorb more, and they found out they did better. And I say older, just a matter of months or maybe a year. You know how some parents always try to accelerate.
I know of this. I don't know. I mean, I don't know the specific study itself and how they studied it, but I know that I've seen parents that have cited that study as a reason for not bringing their kids into kindergarten at 5 years old. They do it at 6 years old.
Yes.
And I'm like,
this was a very controversial thing, and it took some years before some rebuttal got involved there. But it just shows you. I mean, you get, and that was only one thing in that. I forgot the name of this book, but that was only one of the case studies that they presented. Okay. Can we take a mental break for just a second and talk about memory lists? Let's take just a little mental break for a second. What would it mean for, what does this mean? Are we talking about a old folks home or something here or something? Assisted living? No. This is, for a random variable to be memoryless, what does that mean? It means it's the probability that an event occurs in the future. The past history has no impact on it. So it's like, okay, let's do a logic problem here, okay, involving this. So suppose there's a bank and situation, and there's two tellers, and they're both occupied, and somebody comes into the bank, Mr. Smith. Now, the question is, let me get the exact wording of the question. So how many customers do we, okay, so how many customers is counter? This one is being served, this one is being served, and this new guy that's coming in. So there's 3 customers. So the question is, what is the probability that Smith is the last to leave? Okay, now the waiting time will assume this exponential random variable, which I haven't explained, but it's a memoryless. Okay, so whatever the wait time, it has nothing to do with, it's not influenced by how long you've already waited there. So that goes for everybody here. So what do you think this probability would be that he's the last guy to leave? I mean, he's certainly the last to show up. What is the chance that he's the last to get out of there? We have to break this down a little bit, okay? So again, the wait time is exponential, which we don't know, but it's memoryless. Okay, it doesn't matter if he's waited 5 minutes. The probability of waiting 5 more minutes is the same. Okay, regardless of what happened prior to. So what do you think would be the probability here that he's the last guy to leave? Well, how do we break this problem down? So first of all, do you understand the setting that bank with 2 tellers and 2 people that are currently being served, and he comes in. So think about it. I'll give you guys a second. Let me get a drink of water and think about that. Okay, time's up. Now I really sound like a teacher, right? Okay, so anybody have any idea of what the answer might be? Or maybe I didn't give you enough information.
I feel like there's not enough information, or we're going to have to kind of define some things. But, is this a problem from the book?
Yes, but I don't want to.
Okay.
I didn't want to reveal that. Somebody asked me. I didn't want to reveal it.
Before the end, can you at least let us know what the problem is so we can wrap
Yes, but I don't want to. I don't want to. Somebody's going to switch.
That's fine.
There. So let's go over. I claim that you do. In some sense, we have enough information as long as the wait time is memoryless.
Okay.
Because let's break this down. What has to happen first before we start talking about who's going to leave? Who's going to leave last? Who's going to leave first, right? I mean, it's kind of, for him to be served, one of these 2 people has to be done, right? Mm-hmm. One of those 2 has to finish before he can, stop waiting and start getting served by the teller, right? Is that clear? There's 3 people.
Okay, yeah, good so far.
He can't, there's no way he's getting in here unless one of these people goes out. So we can simplify the problem by saying, look, this person is gone, and he's not going to. that person's not going to be the last out. They're going to be the first out of there. Okay, and then what? So he goes over here. Right. Now what? You might say, the intuition would say, this person's been here. You guys have experience with banks? This is a true story. You don't know. The amount of time somebody's going to be, come into the bank, is going to be the teller, doesn't really matter how the way it's distributed, how long they've been there already. It's just the way it is. It's a true fact, you know. But anyhow, so that
No,
guy's
we're saying
gone.
that the time that the person's at the teller is memoryless. So what that implies is
The wait time they will now get before service. The wait before they're done. So the wait time until they're done.
okay, but like the amount of time that someone's been at the teller. We don't know how much it is, but is that amount of time memoryless?
Yeah, well, yeah. I mean, it's memoryless means that what?
It means that regardless of how long they've been at the teller, we're still
same distribution. It's going to be the same distribution. So so if you do it conditionally, it doesn't matter how long they've already waited as to how long they will continue to be there.
I know that because I'm familiar with memoryless. I don't know about everybody else though. Yeah.
Well, but people are familiar with banks, and I'm telling you, this is
okay,
a good model. You never can tell. You never can tell. You think, well, that person's been there a while. It's time for them to go, but then they're there for a lot longer.
Right.
So this person goes. So definitely, it's not that person's not the last to go. Now it's between Smith and this person. But you see, the amount of time that they're going to be there it doesn't have anything to do with how long they've been there. Now these guys have the same distribution. So it's the same. They literally have the same expectation of time to spend before they're done. So that's how we get that it's 50%. It could be either this or this. They both have the same distribution.
Okay. Yeah. So once Smith comes up to the teller, they're both people now have an equally likely chance of leaving
because they have the same distribution. They have the same distribution for going forward, because it doesn't matter that the past history here doesn't matter.
Right. Okay. So yeah. So the person at the teller, yes, that is. We say that's a memoryless distribution of how long they're going to be there.
Yes.
Okay.
So we did the problem. There's no math involved. I guess you could calculate, but that's the answer. The answer is a half. Okay, now I'll tell you where it is in the book. It's example 5C. Now, I know there's no math involved. I haven't given you the distribution, but I'm trying to engender some interest in this exponential distribution. I mean, it's non-intuitive, but I'm telling you that the Poisson distribution, for the radioactive decay of what do you call it, isotope, goes the same way. Just because it hasn't decayed for the last couple centuries doesn't change the probability that it will decay in the next second. I mean, this is just something about physics or the world or the universe that's embedded in this. It's sort of interesting. You might say, well, is it going to decay? Doesn't it sort of accrue instability as it goes? Like, don't earthquakes?
It feels like there should. Yeah, it feels like, it hasn't happened. It's got to happen soon.
Right.
No, because
it doesn't happen. Yeah. It doesn't happen. Now, earthquakes, and this is an interesting thing, because earthquakes get modeled by the Poisson also. And this bothers me because I think of earthquakes as accumulating strain, But, and so if, what I mean? They say, well, we're due for an earthquake on the San Andreas Fault. Well, apparently, I've actually spoken to geologists. They say, no. You don't know when it's going to, it could happen tomorrow. It could happen 1,000 years from now. I mean, they actually model with the Poisson distribution, which surprises me. Okay, guys, let's get off that and let's have a little bit of fun. I sometimes, when I'm preparing my lectures, I have the feeling nobody reads the book, including the author. So, I want to point some interesting out to you. Okay, I'm going to show you a problem verbatim in the end of the chapter. Let me give that to you. Oh, I have a chat here. I don't know if that's related to what I just started to erase. Oh, which did I say?
That was from earlier.
Example 5. So yeah, example 5. Okay, now this requires you guys to have a copy of the book or a download or something like that. But this is a kind of a laugher. I want to point out exercise 540. Exercise 540 in the book. Maybe I should even give a page number so we're clear of what's going on here. It's page 214. Okay, so what is the problem? What is this problem? It's just a standard problem that sits in the book. And let's see if I remember it. X is uniform, 0, 1, and y is e to the x. And they asked for what did they ask for here? The CDF of y. Okay? Now, that's this. Now, if you would bear with me and look at something else.
So this has nothing to do with the X, what was given?
No,
it's just
no.
the CDF of Y?
No.
Okay.
No, this is... So, if you look at example 2b, and they have the same problem. I should say the same setup, same setting. But their goal is the goal there is to calculate E of y. Okay? But in doing so, their first step is, what do you think? The first step on this example is to do what?
Integrate from negative infinity to positive infinity.
Well,
X.
actually, not the first move, but I mean the first. There's a sub goal that they do. Like there's a sub goal.
Sure, then.
Well, okay. If you wanted to calculate E of expectation of y, okay, y is e to the x. By definition, you would. What is the definition of this?
Integral from negative infinity to positive infinity of x times e to the x.
Okay, you want to use x there? Okay, it's fine.
Is that not the definition? Like I thought that was the definition, or excuse me, of y.
Let's do y. Yeah, let's use y. Otherwise, I feel it's a little bit confusing.
Okay.
Y times f. What this is the density of y, right? I mean, this is by definition.
Okay.
Okay. That's what they want to do. But what is the missing? What's this thing that's going to cause us some? I'm sorry, this is kind of roundabout, but I'm proving a point here that there's a serious disconnect going on. We're in the 9th edition here or something. Anyhow, what is the thing you need here? You need this. How do you get that density function? How are they going to get that density function? They want to compute that thing, the density function of y, but how do they get it? They get it by, well, I'll ask you, what do you think? What would be a good way to get the density function?
Okay, so here's where I'm confused. E to the x, that's the integral of that from negative infinity to positive infinity isn't 1. So
Yeah, but it's from Yeah,
Oh, I see now. Okay, so that X. Okay, never mind.
yeah,
X is-
it's
Yeah.
all of this comes together into a sort. I would consider sort of a fraudulent thing,
Okay.
but anyhow, so this is what Ross wrote it. So he wants that guy right here. The way he's going to get that guy is by differentiating the CDF. So he's going to differentiate f of y of f sub. He's going to differentiate this. The f, the CDF for f. If he differentiates that, he gets this. I guess I should put a y here. Okay, so he's going to compute the CDF. He does it. He computes the CDF, and then that's what he will use to finish off the problem. Do you see some issue here? Here's a problem in the book. They're asking you to compute the CDF of y, but in his process to get the density function for y, he gets the CDF first. So he's already done the problem. I mean, I don't know. It just is. Do you see what the issue is? There's a problem in the book that's been done in the book, which I think is pretty funny. I mean, maybe this is sort of complicated here, what they're doing. If you're going by the definition, we need to have the density function for y. How do you get that? Well, one way to do it is to compute the CDF and take a derivative. Take the derivative of the CDF. That will give you the density function. Maybe if that's unclear, let's do it. Let's do one. This is how this happens. So we'll say f of x.
Real quick though, question about the problem. If we integrate from 0 to 1, if we integrate e to the x from 0 to 1, that's not equal to 1. Do we need to have a scaling factor?
No, can I
okay, whatever. I'll let you do your thing.
Yeah, let's just check this out here. So if I have this, what does that mean? That's minus infinity to a, right, of whatever the density function is for x, right? So I want to get the density function for x, right? So if I take the derivative, this is FDOC2, right? What is it equal to? So this is a calculus thing.
Mm-hmm. That's one of the fundamental theorems of calculus. Good so far.
Yeah. So that's what this is their thinking. In order to do this by the definition, this is what they're doing here. So they're doing that problem. They're doing this problem. They're getting the CDF of y and differentiating that to get this what's in the box here. So they give all the steps. And my promise, it's already been done. They didn't. Somebody didn't proof the book or something like that. They wouldn't have, because there's nothing to do. You just copy what's already in there in the example. But let me try to get to your other question. So.
Yeah. So I'm just kind of looking at the setup here. If x is uniform.
Okay. So let's. If I do this, if I have time, I'll start from scratch on it. But let's check this out. Now, you have a very good question. I did not think about that beforehand. So you're saying, okay, here's a new random variable. So what exactly do you want to do with that?
Well, if I want to make sure that actually is a random variable, and to prove that something is a random variable, if you integrate it or if you take the sum of everything, you should get 1.
Yeah, but it's not okay.
Is that not true?
It's not a random variable. It's the density function. You see, I would need to know the density function of y, and say u, du. I would need to know this, or maybe I could use y here. The statement is it's the density function that integrates to 1.
Okay,
We
it's the
need this.
density. So okay, great. So we don't. This is not the density function.
No. This is a random variable. Okay, so
Okay, got you.
there's three players. You got your random variable, you got your density function, and the CDF function.
Okay, so y is just the numbers themselves. We haven't gotten the density function for it
But
yet.
you must have that density function that's associated. And I think if I may be mistaken, but they're asking for that, right?
Well, they want the CDF.
Yeah,
So
they want the expectation, but in doing so we need the density function for y. So we need. It turns out that it's 1 over y. So I've never done this, so I don't know. This is interesting to me. I didn't think of that, so let me check. What's our time here? 7 more minutes. So yeah, the probability density function of y is 1 over. Let's use x. It's 1 over x. That's what they conclude. Okay, so now you have a valid point. So what is it would have to do with the range of x, right? To get this. What are the various things that can come out of here? So we know x goes between 0 and 1. What is the range of y? What's the space of y? Well, x could be 0, in which case it's 1, and then x is 1, it would be e. So the support for y only exists between 1 and e. So when you're doing this, you have to go from 1 to e. Still not going to get the right thing here. You caught me a little off guard because I wasn't expecting. Okay, so.
No, that works because integral of 1 over x dx. Well, the integral of 1 over x is natural log.
Oh, okay. You caught me off guard, but I'm just going at about what? I'm going at 33 and a third RPM. You're going at 45 RPM.
Yeah.
Okay.
So that equals natural log, and natural log of e is 1. Natural log of 1 is 0. So it works.
It is correct. But do you understand what my issue is? The problem in the back of the book, or in the end of the chapter, has been done in the book. I mean, that's just a sort of a freshman kind of mistake.
Yeah, no, I see you. That's not very good. What probably happened is this example, or this exercise was there, and the example was added in a later edition. I mean, that's my guess.
That's one of the problems with additions, maybe.
Yeah.
But let's see. So suppose you wanted to do this problem. What was the problem now? You just wanted the expectation. Okay, that's what they originally wanted, right? So not 540, but in the book they just wanted the expectation of y. So let's take a look. Let's try to close that door. So you just wanted the expectation. So e of y equals what? Well, what you do is we use a theorem. We use the theorem here. We don't do this by hand, We just use a theorem, and it's just like doing the expectation, right, for the discrete. So how do you calculate the expectation? So this is e to the x. Now that's a function of x. So you can go ahead and put that function in there, dx, but you also need the density of x. Okay, so let's see if I get it right. So this x goes from, let's see, it goes from 0 to 1. Because this density, we already know the density of x. This is this, right? It's 1 between 0 and 1 and 0 elsewhere. And now you've got e to the x dx Now, when you integrate this, what do you get? You get e to the x from 0 to 1. What is the answer? It's e minus 1. Now, this is using a theorem. It's proposition 2.1. And you know what? If you're learning this stuff for the first time, I say forget about proving these theorems. Forget about doing things by hand. Just use the theorem. You know, it's like calculus. You use the fundamental theorem of calculus, right? 1 and 2, and you don't in your mind you don't think, well, gosh, how do I prove this, or how was it proven? You just use it, and so you do this, and it's painless. You just get that expectation. But if you do like they in the example they wanted you to do, there's numerous steps. Among them, finding the CDF for y, or the density function for y, which turned out, I believe, if I'm thinking correctly, was 1 over y. Okay. I hope this was, you guys really probably should read this portion, read around what precedes Proposition 2.1. Let me see if there's anything critical to do in the last 2 minutes. Oh shit, there is something I'm supposed to do. Oh gosh. Okay, let me just introduce this problem. This is important stuff. Okay. 2 minutes, just to introduce this thing. When you transmit information, we all know it gets transmitted in bits, right? So zeros and ones. So if you have a 0, you want to transmit it, or 1, you transmit it. Hopefully, the person on the receiving end sees the 0 as a 0 and the 1 as a 1. What is wrong about this from an engineering standpoint, what I just said? When you transmit stuff, what is the thing that's always there? When you're like on your cell phone or something and you're not getting a really good reception, you got static, right? What do you call that? What do you call that? Noise, right? You got noise. So in an effort to counteract this uncertainty with the noise, what you do is instead of sending a 0, we'll send a -2 on. Instead of a 1, we'll send a positive 2 on. So what I'm looking for here, what I'm looking to receive is this or this. There's some separation between them. Now, the noise is modeled by a normal curve. That's the way it always is. Noise is always, it's normally distributed. This is just the fact of life. So what you really get is -2 plus some noise from a normally distributed thing. And here you get +2 plus the noise. And the obvious question is, since we've got the number separated a little bit here, and it's a standard normal, what is the chance I'm going to get an error? And I think I got a chat. Yeah. What's the chance that we're going to get an error here? Well, it depends. You have to have certain cutoffs. So we'll go into this. But if it departs significantly from -2, you assume it's the other number. You know, it's not 0. It's the other number, and you have to have these preset decisions which are going to do when you don't get exactly -2, you don't get exactly +2, and the question becomes if this noise is normally distributed, n is a standard normal. If it's a standard normal, what is the chance that we, subject to our interpretation cutoffs, what's the chance we get an error? So I don't know that. Let me see if I can recall it. If it's a 0 and you get greater than a half, so if this is greater than a half, then you think of it as they meant to send a 1. Okay, so that's an error. This whole idea of, now I'll stop here, the whole idea of how to handle error and information just by itself, all information has mistakes in it, you know what I mean? DNA has mistakes. How this is done in nature or in electronics, information, how this noise is handled is very interesting subject. They might say, well, redundancy is the way to go, but there are more clever ways of handling this problem. Like if you have a long sequence of zeros and ones, I mean, you need some self-correcting code or something. If there is a mistake made, that it will be noticed. And this is fascinating stuff. And biologists worry about this. Think about these things. Okay, guys, I think I've gone way over the limit. I meant to do this problem first. I'm sorry. We'll pick it up on Tuesday. Anybody going to the math open house tomorrow? Want to see anybody? Zumi, the math open house.
I got an email about it. Let me look at it and when it is.
They have people who've gotten degrees here, and they work in industry or in teaching, community college, or even higher. Some are administrators now. Somebody's a vice provost at Pierce. They interview these people, and it's live, so you'll be able to ask some questions and stuff. And so it's kind of like, part of it is like, one part is, what research are students doing in the department, what research are faculty doing, and then alumni, what are they doing? What are they up to? And how do they use their math background in their jobs? Does everybody understand? Can everybody hear me? We're down to 15 people, but I hope especially if you're a math major, CS, I can understand it. But if you're a math major, you really should go to, and there's a blues band too. One of my colleagues has a blues band, and they always perform. So I guess they'll have to do it on Zoom. But the neat stuff is it's live music, and he composed some of the songs himself.
Cool. Yeah, I'm looking at it, and there's a schedule for it.
When does it start? 11 or 10:30?
It starts at 11. It goes all the way to 6.
Yeah, nobody has 7 hours to blow, but maybe you could just hop in on the blues band,
Yeah, it's neat.
Yeah, we had it 2 years ago or a year ago. We had it live here in the student union, one of those rooms, and there were good eats. There were eats, and there was the music, and I just had a good feeling about it, and the I don't know, just it was worth, it's a lot of work to put this thing together, and I didn't do any of it, but to hear what people are up to after they get their degrees, and what they've been doing, it's amazing. These math majors are all over the place. Some of them are working for the city, some for the county, and they're not doing what you would think of as traditional math kind of jobs. It's just that they were trained in a way that they can fit in a lot of different situations, a lot of settings. Of course, the CS majors are probably think I'm full of it here because they know what they want to do, But does computer science have an open house with a band?
I don't know. I mean, obviously, I don't know, but yeah, I have a lot of work tomorrow, but I might be able to come to like the first bit of it for the faculty research presentation.
Are you like a tutor, professional tutor? I forgot what you.
Yeah, so I'm a professional musician.
Oh, the one with the viola?
Yeah.
Oh, I thought that was somebody else because you don't use that anymore. You don't use that.
Yeah, I had to change it for they wanted like just a headshot and nothing else for my my field experience class. So if for any reason cameras needed to not be on, they could still know who you are. So yeah, I had to change it. I mean, CSUN was fine with it, but it was just specifically for the high school that I'm doing stuff. So yeah, so I'm a professional musician, and I do math tutoring for a private school for students with learning disabilities. And then I also just do, I do music lessons and math tutoring for just people who want it. But, that's just contract work whenever I get it kind of thing.
Well, I mentioned if you're a professional, it's at least $50 an hour to teach the instrument, right? At least.
Yeah, that's what I charge. So,
yeah, my son's bassoon teacher was $50 an hour. Yeah.
If I got some if I majored in music, I could charge even more. But I'm not self-taught. I just haven't gone to a university for music
or conservatory.
Yeah, so I've worked just with I've taken music lessons all my life, and I'm still taking music lessons now.
Is your teacher on the LA Philharmonic or something like that?
I'm taking harp right now. I change well, I don't change instruments. I just get new instruments. I like strings. And I'm working like I found my teacher through the music union, like the orchestra musicians union, and she's fantastic. She does all these recording jobs. Like if you've ever heard harp being played in a movie or a video game that was made somewhere around Los Angeles, wow. It was her. She did it. So anyway, she's fantastic. You know, like she sees that what I'm trying to do with music is more of a hobby, and my career thing that I want to be doing is math.
So she's a studio musician, is what you would say, yes. Right?
She is.
Those are good. Those pay pretty well, right? I mean, that's pretty good stuff.
Yeah. Well, I mean, I would know. So I get some work for it sometimes.
But are you union or whatever that is? SAG?
Yeah. Oh God, what's the name of the union? The Orchestra Musicians Union. It's statewide. It's all through California. But if you wanted to get a job working in like basically anywhere that's like a movie, it's always union work.
Yeah.
So it's good to pay your dues so you can get those jobs.
My ex, her stepfather, who she grew up with, he was Aaron Spelling's music editor. So he did all the lots of stuff, you know. And so I've heard all the stories. And you can make at that point anyhow. You can make good money if you're.
You can. And you know, and every so often I get a call just because your name is just in the book. You get a call that just says, "Hey, are you available at this time? Can you do this recording? This is the whole thing." And so you just go do it. It's nice, but you know, like right now, there's no work. It's just there's nothing. So I'm kind of glad.
You can join this blues band, you know. they need some string person. They need that, you know.
well, I'm going to be learning bass soon, so there's something.
Or if you get good at the harp, that somebody could call you up and say, "We need somebody for that solo beginning of Death and Transfiguration." You know that harp solo there. That's a beautiful, beautiful solo in the beginning of Death. You know, Richard Strauss.
So I mean, yeah. So I'm glad that I've got math right now because people are still in school. Granted, a lot of before the pandemic hit, I would get people who are fine in math and just wanted to brush up on things like, oh, I've got an AP exam coming up. Oh, I want to get ready for the SAT. I'm not getting any of that. I'm only getting the students who are like, I'm going to fail. I need help right now. And I will do my best. But if you're calling me in April, I'm sorry. There's only so much I can do.
Well, I have a friend who was a professional tutor, and I did a little bit of tutoring when I was a grad student. One of the problems is the parents, wealthy parents, give the kids money for tutoring, and the kids spend it. They don't tell their parents, and so you get I get a cancellation like just a few hours before the appointment. Yeah,
that has happened to me. Thankfully it doesn't happen too much, and in most cases it's the kids asking their parents, I need help, I want to work with a tutor, can you get me a tutor? And that's the best situation because they genuinely want to work with you. But then I have a couple students where it's the parents that want to get tutoring for their kid, and the kid is like, no. And I'm like, God, this is the worst.
I had to walk away from one of those because I felt bad for the student, and I said, I can't take your money. I can't take your parents' money because the kid was not motivated. I just couldn't do it. And they were surprised. They were really surprised that I would walk away. But I just, you know what I mean? I want to be able to sleep at night.
Yeah. And not to mention, if I wanted to get into another field that made more money, I could. Like, I genuinely feel like I probably can go work for Boeing or something like that if I wanted to get into engineering. I don't want to because I love teaching. So whenever I've got a student that just genuinely doesn't want to learn, they're not motivated, they're like, you know what, I would rather just barely pass math and just get on with my life. I don't want to work with that kind of student.
Yes.
So, and I can choose not to. Granted, if I'm teaching K through 12, I can't choose not to. I know, I'm well aware. But for tutoring, at least, where I'm literally just working with the one student, if they are basically just asking me to do their homework for them,
Yeah.
I just tell the parents, look, at this point, it's not about tutoring. It's about you're going to have to talk to them about like getting them motivated to at least pass math, let alone actually care about it or anything.
Unfortunately,
that's not my job. I'm not good at that.
Right, but the parents don't know the difference sometimes, right?
Oh yeah, you're right. They don't know the difference.
Especially if they're wealthy, really wealthy. They think money can solve every problem. Just throw some money at it.
Right. Yeah. Well, you're excited about math. You should be able to get them motivated. I'm like, there are some kids where it's a lost cause. I'm sorry. So,
yeah. I hear you. It's I hear you.
I have to go to my next class. Take care.
All right. Nice talking to you, and thank you again for your participation. I'm sorry I was all over the place, but I don't know.
It was a little hodgepodge today, but it's okay.
Yeah, it's hodgepodge. I'm hodgepodging.
And I will say for review, the one thing that generally speaking I really like about review is do a problem but change it somehow. So because that's what's going to happen for the test. So you're not going to give us a problem that's exactly the same as something we did in class, but if you can show us multiple ways that we could see a topic, that really helps with how it's going to show up. So like really, we don't mind review. It's fine.
Okay.
As long as it's like a way to, manipulate the problem. So just saying.
You had a lot of good questions. You had a lot of good comments about this. The fact that thing was a density. That was good.
Well, yeah. I genuinely I don't get it. So it took me a second.
Yeah, it took me more than a second. So yeah. Okay.
No, seriously, I gotta go. My class.